A prior existence in a few billion years, scientists predict that our universe may face a catastrophic event known as the Big Crunch. This is when all matter, stars, galaxies, everything, will start collapsing back into a dense state, leading to an intense high-energy ending. But what if that's not the whole story? According to Professor Roger Penrose, our understanding of the universe's end may be far from complete. He proposes that in the distant future, another Big Bang could occur. I've come to the view that there was something before the Big Bang and it goes on expanding. It's now indulging in what's called the exponential expansion, which is caused by what people call dark energy, Penrose states. In other words, he argues that the Big Bang isn't a one-time event but rather an optical illusion of sorts. The universe might go on forever, not in a repeating cycle of Big Bangs and Big Crunches, but in a continuous and unending sequence. He even boldly claims that there is evidence of a previous universe existing just before ours. He said with great certainty, the evidence for it is really quite strong. The strength of the signal we see is at a 99.98% confidence level, which is pretty strong. A single black hole gradually swallows most of the cluster, and all that energy bursts through onto the other side. So, what is the piece of evidence Professor Penrose is claiming, and what could it mean for the distant future of our universe? Back in 2019, Roger Penrose co-authored a research paper published in the Royal Astronomical Society titled Apparent Evidence of Hawking Points in the CMB Sky. In this paper, he and his team claimed to have found several anomalies, potential evidence of a universe that existed before our own. As stated in their research, each anomalous spot would have originated from a highly energetic point-like source, resulting from the Hawking radiation of supermassive black holes in a cosmic aeon prior to our own. Simply put, these dark spots may represent actual evidence of a previous universe or, as Penrose describes it, an aeon rather than a universe. This idea falls under the framework of conformal cyclic cosmology, CCC. It replaces the traditional inflation model with a lambda-driven exponential expansion of a universe epoch referred to as an aeon. In this view, our universe is one in an endless sequence of aeons, each starting with its own Big Bang. The lifespan of each aeon could stretch up to a googol years. If time truly extends infinitely, the idea is that another Big Bang would eventually occur in this remote future. The ultimate fate of black holes becomes significant. Penrose suggests that some of these supermassive black holes from a previous universe might become bound to the conformally stretched Big Bang of the next aeon. The observed anomalies are proposed as evidence of this connection. However, these claims are highly controversial and not widely accepted within the cosmology community. Where's the evidence? How does one argue that these spots are definitive evidence of black holes from a prior universe? It all circles back to a concept long proposed by the late Stephen Hawking, known as Hawking radiation. The premise is straightforward. We are able to observe dead black holes left behind by earlier aeons. These black holes, possibly as massive as \10^14 times the mass of our Sun, would have evaporated through Hawking radiation. In this grand concept, these remnants would form what is referred to as a Hawking point. Penrose described these warm points as being about 8 times larger than the diameter of the Moon. He elaborated in his paper, "We must bear in mind that despite Hawking radiation being of an absurdly tiny temperature, over the aeon's history, the entire mass energy of the black hole will be finally radiated away. In the conformal picture, this will take place within what would effectively be a single Hawking point. Given that the Hawking evaporation of a supermassive black hole would generally take much longer than the current age of our universe, some information from a previous aeon may seep into the next cycle." His team identified several characteristics of these Hawking points as anomalies in the CMB map, challenging Penrose's CCC. Penrose reiterates his belief in what he humorously calls a crazy theory of mind. He suggests that our universe will continue to expand until all matter decays, and then a new Big Bang will occur. However, remnants from a previous aeon may occasionally seep into our current one. The biggest difference in predictions between CCC and inflation theory lies in what we should expect to see. CCC suggests that we would find imprints of a universe before the Big Bang visible in the large-scale structure of our universe and in the CMB. In contrast, inflation theory posits that any point where inflation ends and a hot Big Bang begins must be causally disconnected from other regions. Observations from missions like COBE, WMAP, and Planck have consistently supported inflation, not CCC. Many scientists argue that Penrose's claims rely on a flawed interpretation of the data. Despite this, Penrose continues to advocate for his CCC idea, humorously noting, "I could go on lecturing about this forever because nobody will ever know whether it's right or not." Interestingly, Stephen Hawking had a different view. He believed in a multiverse of many universes, each with different laws, rather than Penrose's cyclic cosmology. As Hawking stated, our cosmic habitat, now the entire observable universe, is just one of many. In this context, the concept of a galactic multiverse arises. After an unimaginable period of a Google years, a new aeon begins, and the cycle continues endlessly. This raises profound questions about the nature of existence and the mysteries of time. If the universe continues on for eternity, would it eventually lead to another Big Bang or perhaps a Big Crunch? What are the consequences of such an endless cosmic cycle? To address these questions, we need to revisit a concept known as the phase-space volume. This is a theoretical space that represents all possible states the universe can exist in. Its volume is an astonishing ×10⁻123 cubic meters, so vast that it defies conventional understanding of scale. By contrast, our current observable universe, the part we can see with telescopes and instruments, is around ×10⁻26 cubic meters in volume. While this might seem unimaginably large, it pales in comparison to the theoretical size of the phase-space volume or even a Googleplex universe as previously discussed. Now imagine a hypothetical universe extending a Googleplex meters across. If you were to traverse such a vast universe, you'd eventually notice something peculiar. Repetitions, not just ordinary repetitions but exact copies of yourself. This phenomenon arises due to the concept of quantum states. A quantum state is essentially a specific arrangement of particles and fields in a defined system. In the context of the human body, this means considering the unique arrangement of its atoms and particles, everything that makes you you. The total number of quantum states that describe the space you occupy is approximately ×10⁻10⁻70, assuming you occupy about 1 cubic meter of space. This number is derived from the combinatorial possibilities of arranging particles under maximum entropy in a system constrained by the Heisenberg uncertainty principle. For example, in black hole thermodynamics, Stephen Hawking and Jacob Bekenstein found that a black hole's entropy is proportional to the surface area of its event horizon. Similarly, for ordinary volumes of space, the number of quantum states depends on the volume and the forces within it. If you occupy a space of about 1 cubic meter, there are ×10⁻10⁻70 possible quantum states for that space. This means there are that many different versions of you in terms of atomic arrangements, some resembling celebrities, animals, or even unrecognizable forms. Despite these colossal possibilities, the number is still far smaller than a Googleplex. In a sufficiently vast universe spanning a Googleplex distance, repetitions of your atomic arrangement are inevitable. Traveling a Googleplex distance could lead you to encounter another version of yourself, an exact copy with the same brain chemistry, thinking processes, and behavior. In this hypothetical multiverse, not only could there be endless versions of you, but also endless variations of everything else. Every possible arrangement of particles, history, and future would exist somewhere in this vast expanse. Rewinding the universe's clock far enough brings us to conditions of extreme density, temperature, and energy. These conditions approach what is known as a singularity, where conventional physics breaks down. At approximately 13.8 billion years ago, we reached the Planck era, exactly ×10⁻43 seconds after the Big Bang. The Planck time, the shortest measurable time interval, is a staggering concept to grasp. Its brevity is almost unimaginable. Consider that the universe's age is nearly 14 billion years. If this age were a single unit of time, more Planck times fit into 1 second than there are seconds in ×10⁻22 universes of this age. To further illustrate, imagine the Milky Way with its 100 billion stars and the observable universe containing 2 trillion galaxies, each with about 100 billion stars. If every star had 300 identical Earths orbiting it, the number of grains of sand on all these planets combined would still be far fewer than the number of Planck times in a single second. The Planck time is the universe's frame rate, while the Planck length represents its pixel density. During the Planck era, the 4 fundamental forces, gravity, the strong and weak nuclear forces, and electromagnetism, were unified as a single superforce, similar to how water exists in different phases. As the universe expanded, these forces separated during phase transitions, and particles and antiparticles were created in great numbers, annihilating each other into radiation. By about 380,000 years after the Big Bang, the universe cooled enough for neutral atoms to form, allowing stable structures to emerge without being destroyed by high-energy photons. The inflationary theory predicts that at very high energies, forms of matter could reverse gravity, causing it to behave repulsively. This repulsive gravity is hypothesized to be the bang of the Big Bang, setting off a rapid inflationary expansion of the universe. Approximately 55 years ago, the cosmic microwave background radiation (CMB) was detected, providing strong evidence for the Big Bang theory and solidifying it as the leading explanation for the universe's origin. However, alternative models like the steady-state theory, championed by figures such as Fred Hoyle, resisted this paradigm shift. Despite accumulating evidence over time, these contrarian views faded into obscurity as they failed to match observational data. Following the evidence, could Roger Penrose's conformal cyclic cosmology (CCC) face a similar fate? While intriguing, his claims remain controversial and lack broad acceptance. Finding patterns in CMB data demands caution, as seen in debates sparked by the BICEP-2 experiment and its findings of B-mode polarization. Misinterpreting patterns can lead to overreaching conclusions driven by imagination or flawed algorithms rather than genuine evidence. From the 1960s onward, cosmology has made significant strides in understanding the universe's growth, evolution, and fate. Yet mysteries remain, challenging the Big Bang theory's predictive power. These gaps highlight areas where unknown factors might exist beyond our current understanding. Science offers two paths: inventing new mechanisms to explain these phenomena or assuming the universe was born with the observed properties. Only the first approach holds scientific merit as it pursues evidence-based understanding, even without immediate results. Ultimately, the universe itself will reveal what is true and what is speculation.